Hello students, Secondary 1 Chemistry. Today we are starting to study Nuclear Chemistry, Unit 5. The lesson now is isotopes, atomic masses, and energy mass interconversion. We know from the preparatory stage that the atom consists of a central nucleus, and around the nucleus there are negatively charged electrons, but inside the nucleus there are many protons and neutrons. The smallest atom contains one proton, as in the case of hydrogen atom, which contains only one hydrogen, one proton, and the other elements contain more than one proton. Also inside the nucleus there are neutral particles called neutrons. So inside the nucleus there are protons and neutrons. Protons are positively charged particles, neutrons are neutral particles. Outside the nucleus there are electrons, one electron or more electrons. The charge of the electron is negative, and its location is around the nucleus. Inside the nucleus there are protons positively charged and neutrons. Here is what is known as the nucleus symbol. If the element contains a number of protons, the number of protons is called atomic number. Atomic number is the number of protons. There is also a term called atomic mass or mass number. This mass number is the sum of protons and neutrons. So the nucleus symbol X, here is the Z, which is the atomic number, and A is the mass number of protons and neutrons. For example, if we want to write the nucleus symbol of sodium, for example, sodium atom contains 11 protons and 12 neutrons. So the symbol is X11, and above Na there are 23 particles, number of protons and the neutrons. The nucleus of sodium contains 11 protons. What is the probable symbol? Of course, the probable symbol will be like that in D, because there are 11 protons and this is 23, the number of protons and the neutrons. Why this is not the answer? Because the number of protons is 11, but the sum of the number of protons and neutrons is 9, which is impossible. So this is not the answer. The answer is D. There is also a term called isotopes. Isotopes are atoms of the same element that have the same number of protons, or the same atomic number, and different number of neutrons, so they have different mass numbers. For example, hydrogen isotopes H11, H12, H13. The three atoms are of isotopes of hydrogen. The number of protons is the same, 111, but here there is no neutrons, 0 neutrons, so the atomic the mass number is 1. Here is the mass number is 2, the mass number is 3, so here is 1 neutron only. Here is here 2 neutrons. Another term called quark. Quark is the unit of large particles such as protons and neutrons. But electron is a primary particle, but proton consists of 3 quarks. Neutron also consists of 3 quarks. What is the quark? A primary particle that cannot be existed alone, and all nucleons are formed from this quark. There are 6 types of quarks: U quark or upper quark, down quark, top quark, bottom quark, strange quark, and charming quark. The most important types of quarks here in our syllabus is the U quark or the upper quark and the down quark. The quark U quark charge is +2/3, while the charge of the down quark is -1/3. The proton consists of UD quarks, UUD quarks, and so its total charge is +1. When you add +2/3 +2/3 -1/3, you get 1 +1. So the charge of the proton is +1. While the quarks of neutron are DDU. 3 quarks. D is -1/3, another D -1/3, and U +2/3. So the total charge of the neutron is 0, which means that neutron is a neutral particle. Here this figure shows UDD, which means that this represents a neutron. The answer here is neutron. If you want to calculate the atomic mass, it is known that each element in the periodic table contains a number called atomic mass, which was used in the first term to calculate the molar mass of any substance. Atomic mass was given between brackets when you calculate the molar mass of the substance in the first term. Okay, how to calculate the atomic mass of any element? Atomic masses are present in the periodic table for each element. Atomic mass of any element is the sum of the relative atomic masses of each isotope multiplied by its percent abundance over 100. Okay, so for example, if you want to calculate the atomic mass of europium element, EU, europium element contains 2 isotopes, okay, EU 51 and EU 53, 153 and 151. The relative atomic mass of the first isotope is 151 U, atomic mass unit, and the relative mass of the second isotope is 153 U, atomic mass unit. The abundance of the first isotope is 47.77%, while the abundance of the second isotope is 52.23. It is required now to calculate the atomic mass of europium. When you want to apply this law to calculate the atomic mass of europium. Multiply 151, which is the relative atomic mass of the first isotope, by 47.77, which is the percent abundance of the first isotope. Then plus sigma, this is sigma, so plus 153 multiplied by 52.23 over 100. Okay, then use the calculator to find the answer. So it may be around 152. This is the answer of this question. In the same way, nickel contains 4 isotopes. This number is the relative atomic mass, and these numbers are the abundance of each isotope. So multiply each one, 57.935 and so on, by 68. So multiply the relative atomic mass for each isotope by its abundance, then this number by this number, plus this number by this number, plus this number by this number, and so on, over 100, and use the calculator. Einstein discovered that it is possible to convert mass into energy and vice versa. You can also convert energy into mass. The relation between the two quantities, mass and energy, is called Einstein Equation. Einstein Equation is E equal mc square, where c is the velocity or speed of light, m is the mass in kilogram, and E is the energy in joules. This is another form for Einstein equation, E equal m by 931, where m is the mass in atomic mass unit, and E is the energy is in a million electron volt, MeV. This is also another form for the interconversion of mass unit and energy units. 1 AMU equal 1 U. U means atomic mass unit, equal 1.66 by 10 to the minus 24 grams, equal 1.66 by 10 to the minus 27 kilogram. These quantities are equivalent to energy units, 1.49 by 10 to the minus 10 joules, which is also equivalent to 931 million electron volt. It is possible by using this relation in the rectangle to convert mass units into other mass units, and mass units into energy units, and vice versa. Okay, so we can use these relations to calculate the conversion of mass into energy or energy into mass. You can use any law of the three. You can use this one, you can use this one, and also you can use this one. But this rectangle is more common. It can calculate most of the problems, as it is here in the following example. Calculate the amount of energy produced from the transformation of a mass of 1 gram into energy, given that the speed of light is 3 by 10 to the power 8 meter per second. You can use this law. Also you can use this law. Substitute by m by 1 over 1000, because m here must be in kilogram, but here the unit is gram. So 1 over 1000 is m, multiplied by the speed of light, 3 by 10 to the 8 square. Okay, you can use the calculator to find the answer. The answer will be in joules. Also, you can use this relation by putting here 1 gram. Put 1 gram here, down the grams, 1.66 by 10 to the minus 24. Put 1 gram here, and put here, if you want to get it in joules, put x here. If you want it in million electron volt, put x here. Then use the mathematical relation by multiplying means and extremes. You can find the value of x, which is the required quantity. Okay, and in this way you can calculate any interconversion between the mass and energy. Okay, now this is the last one, and thank you for listening.